Okay. So, last class we talk about the discrete time Fourier transform. Now we talk about discrete Fourier transform. So, this class talk about the discrete Fourier transform. So, what is the difference between DTFT and DFT? Here I said discrete time Fourier transform. Signal in time domain signal is in discrete form, but the frequency response is h or x of e to the power j omega continuous. But here I am saying discrete Fourier transform. Here both the signal and frequency domain representation both are discrete. So, if I say both are discrete, so I know how to discretize the analog signal I know. So, suppose I have a signal x of t, you know that x of t is discretized by x of nt, that capital T is called sampling period. So, I have a continuous signal, I am discretized the time instant, and the difference is called t. So, that is why I said x of n is equal to x of n into t. Okay, discrete signal I have known. And if I take the Fourier transform of x n, I get x of e to the power j omega, which is continuous in frequency domain. Frequency is continuous, frequency is not discrete. So, as you know that suppose I have a signal like this is my signal frequency response, this is my signal frequency response, this is Fm, maximum frequency, let us say, or this is omega m, maximum frequency content in the signal. If I take the frequency response, I know it will look like this. This is omega m and this is 0, this is minus omega m. This is omega axis. Similarly, here is let's again this is Fs omega s, or which is nothing but Fs is equal to 2 pi, omega is equal to 2 pi here. Then again I get this kind of same response. This is omega s plus omega m, this is omega s minus omega m. So, that kind of frequency response we get. Now, what I want discrete in frequency domain also. So, x of e to the power j omega has to be discretized with x of k. So, k is called discrete frequency like n. As I said, n is called index. So, I said I have taken the sample time, I have sampled the signal with a t interval of time, and each of the interval is represented by an index which is called n. So, xn is called discrete signal in time domain. Now, I have an x of e to the power j omega, I want to sample it in frequency axis also. So, I have an omega axis, so this is my omega axis. I want to take the sample in here also. So, how do I do that? Here I said t is the sampling period. Here also I have to define certain t. So, as I know that, forget about this slide. This is my omega axis, and I know if this is 0, this is 2 pi, and if my omega m is the maximum frequency, then the signal is represented, frequency represented like this way. So, e to the power x of e to the power j omega is my, this is the x of e to the power j omega. This is pi, this is minus pi. let's say, sorry, this is like omega m and this is minus omega m, and this side also there will be a minus 2 pi. Okay, so this is 2 pi. Again it will be repeating here 2 pi, this is 4 pi. So signal is repeating, e to the power j omega has a period of 2 pi. So if it is e to the power j omega has a period of 2 pi, then if I want to make it discretize, I have to only consider this part only sufficient, and then next part will be just repeat. So I want to discretize this one 0 to 2 pi, the variation of this omega. Let's say I want to discretize in a n number of discrete value. So I have a 0 to 2 pi and I divided into n number of discrete value, n number of value. So instead of writing x to the power e to the power j omega, I want to write x of k, where k varies from 0 to n minus 1. N number of division I have made. Now what is the value of each division? The total value is 2 pi and n number of division I made. So total length of each division is nothing but a 2 pi by n. So I can say e to the power j omega, e to the power j omega is nothing but e to the power j 2 pi. So 2 pi by n. Now what is the index is having? K multiply by k. So instead of writing x to the power e to the power j omega, I am discretize that, which is x of k, which is nothing but a e to the power minus j 2 pi by n into k. Then I said xk is also discrete. So I can say discrete Fourier transform. Then what should be the expression? Forget about this part. So what is the expression of DTFT? Discrete time Fourier transform. I know x of e to the power j omega is nothing but a n varies from minus infinity to infinity, x of n e to the power minus j omega n. This is my discrete time Fourier transform. Now what I have done, I have divided this omega, the scale, with a n number of points. So that is called length of DFT, length of discrete Fourier transform. So I can say x of k is equal to, so I said n varies from 0 to x of n e to the power minus j 2 pi by n into k into n. 2 pi by n into k is the omega and into n. Now what I am considering here? I am considering signal is periodic at n point. Because when I divided the frequency scale, I said 0 to 2 pi, 2 pi is the period. So I am considering that in frequency domain, the signal is forcefully periodic at 0 to 2 pi. So n is the period. So this is the expression for DFT, discrete Fourier transform. The consideration is that whatever I said, the n is the period of the signal. Even if the signal is aperiodic, I can say forcefully n is the period of the signal. and that n is called n point DFT. So when I say n point DFT, that means I am divided the frequency scale into n point. N is the length of DFT or DFT length. Is it clear? So discrete Fourier transform will define by x of k n equal to 0 to, sorry, it will be n minus 1, because 0 to n minus 1. So n equal to 0 to n minus 1 x of n omega n k n, which is nothing but a e to the power minus j 2 pi by n number of division into k is the index, and multiply by the n index. So you don't have to remember it. You can derive it using logic. Don't remember it. If you remember it, you will forget. So think about what is the basis of the frequency transform? This logic you remember, that I have a signal. The frequency transform means the signal has to be convolved with a sinusoidal component. So how do I represent a sinusoidal component? E to the power minus j theta. It has to be e to the power minus j theta. It has to be convolved. Convolved means summation sign is required. So that's why n equal to minus infinity to infinity x of n e to the power j omega n. Now when I say discrete Fourier transform, so I said discrete Fourier transform, that means the frequency domain also I am discretized the signal. So e to the power j omega has to be discretized. How do I discretize? I have to sample it. So how do I sample it? I said 0 to 2 pi is the frequency range, and I have divided this range by n number of samples. So I can say 2 pi by n is the each of the sample width, and index is k. So I can generate any sampling frequency using the index of k. I just replace that things with that, I get the discrete Fourier transform. Okay. Then what is the inverse discrete Fourier transform? IDFT, inverse discrete Fourier transform, because I get x of k when I x of n DFT, I get x of k. Now I can say x of k IDFT, inverse discrete Fourier transform, I should get x of n. So what is x of n? Equal to 1 by n, k equal to 0 to n minus 1. Now x of k, so it is of d omega. So d omega is nothing but a x of k with respect to e to the power minus j 2 pi n. So if it is minus, then minus minus it will be plus. So it will be plus 2 pi n by k n. So in summary, what I can say, the equation of a DFT equation, okay, I will take another slide. So in summary, what you have to remember is that I said DFT equation x of k is equal to n equal to 0 to n minus 1 x of n e to the power minus j 2 pi by n into nk. What is the IDFT? DFT, discrete Fourier transform. IDFT, what I get? I get x of n. How do I get? 1 by n, this is normalization, n equal to 0 to n minus 1, input is x of k e to the power j 2 pi by n into nk. So this is the IDFT. Okay. So let's do some example, then we'll come back again the properties kind of things. Let's do some example in here. Here itself I can take some example. Let's say I have a signal x of n is equal to, let's say 1, 2, or let's say 4 point DFT. I said forget about this, 1, 2, let's say 3 and 4. Okay. Now I want to take 4-point DFT, n equal to 4. I said n equal to 4. Length of DFT length is 4. So, I want to calculate x of k. So, what is the index of k? K varies from 0 to n minus 1. So, here n minus 1 is 3 and signal is varies from 0th sample, first sample, second sample, third sample, 0 to 3. So, what is x of k? X of k is equal to n equal to 0 to 3 x of n e to the power minus j 2 pi by 4 into n into k. So, I can say what is the x of 0? Capital X 0, first frequency component, first frequency initial component of that frequency part. So, what is there? N equal to 0 to 3 x of n e to the power minus j 2 pi by 4 into n into k. So, n is there, k equal to 0. So, I can say this whole part is equal to 1. So, I can say it is nothing but a n equal to 0 to 3 x of n. So, it is just sum. You can say the 0th sample 1 plus 2 plus 3 plus 4. So, it is nothing but a sum of the sample. What is the meaning? Meaning is this is contain the DC part of the signal, no frequency, no e to the power complex part is there. So, there is only the DC part of the signal. So, I can say 3, 3, 6 plus 4, 10. Then what is x of 1? Is nothing but a n equal to 0 to 3 x of n e to the power minus j 2 pi by 4 into n into 1. Now, what is e to the power j minus j 2 pi by 4 is equal to nothing but a e to the power minus j pi by 2, which is nothing but a cos pi by 2 minus j sin pi by 2. So, what is the value of pi, cos pi by 2? Cos 0 1, cos pi by 2 is 0. Sin pi by 2 is 1. So, it is nothing but a minus j. So, I can say it is nothing but a minus j. So, instead of writing this part, I can say it is nothing but a n equal to 0 to 3 x of n minus j to the power n, or I can say minus j to the power n k, because when I say k equal to, so k equal to 1 here. So, I can say it is nothing but a x 0 plus into minus j to the power 0 plus x 1 into minus j to the power 1 plus x 2 into minus j to the power 2 plus x 3 into minus j to the power 3. So, it is 1 x 0. So, 1 plus x 1 is 2 and minus j plus x 2 is 3 into minus j whole square. So, it is nothing but a minus 1 plus 4 into j whole square minus j. So, it will be whole cube minus minus plus j. So, I can say it is 1 minus 2j minus 3 minus plus 4j. So, I can say it is nothing but a minus 2 plus 2j. So, you can say x of 1 is a complex number. So, x of 1 is a complex number which is minus 2 plus 2z, 2j is a complex number. So, I can say what is the mod of x of 1, which is amplitude spectra root over of 2 square plus 2 square. I can say value is 4 plus 4 to the power of 8. Okay. So, what is the theta? Theta is equal to tan inverse 2 by minus 2 is equal to minus tan inverse 1. Similarly, you can calculate x of 2 also. What is x of 2? Again I can say n equal to 0 to 3 x of n. So, I replace by minus j to the power n k, n into k equal to 2. So, I can say n equal to 0 to 3. So, I can say x of 0 multiply by minus j to the power 2, sorry 2 into 0, 0 into 2 plus x of 1 multiply by minus j to the power 1 into 2 plus x of 2 into minus j to the power let us say 2 into 2 plus x of 3 into minus j to the power 3 into 2. So, I can say it is nothing but a x of 0 into 1 plus x of 1 means x of 1 like x of 1 minus j to the square, minus j square means minus 1. So, I can say it is minus 1 plus x of 2 into minus j square of minus j square. So, it is nothing but a plus 1 plus x of 3 into minus j square. So, that means minus j. So, like that you can calculate. So, I can calculate x of 2, I can calculate x of 3, I can calculate x of 3. So, I get the sequence x of k. If I want to plot, I can plot the magnitude spectra. This axis is the k, this axis is the mod of x of k. I can plot it. Okay. Similarly, I can plot that theta part also with respect to k. So, k is discrete frequency. Okay. Now, what is the relationship between this discrete frequency and analog frequency? So, I can say, so this is that relationship you can say, this is the magnitude part, this is the theta part. So, what is the relationship? K is nothing but a, what I said? I have divided 0 to 2 pi in n number of points and k is the index. So, it is k equal to 0. So, any point if k equal to 2 here, I can say that what is the frequency? Frequency is nothing but a 2 pi by n is the division into 2. So, suppose I told you I have a signal, let us take another slide. To understand this part, you have to very clearly understand this part. Suppose I told you in a practical scenario, I have a signal x of n which is sampling frequency for discrete signal is let us say 8 kilohertz. Okay. So, sampling frequency of the signal is 8 kilohertz. I apply a 1000 point n equal to 1000 point DFT. So, I can say x of n is done discrete Fourier transform where n is equal to 1000, I get x of k. Now, if I told you, can you plot this axis is the frequency f and this axis is the mod of xk. So, what is the relations between the k and f? Discrete frequency and the frequency component of the signal. Let us say xn has a frequency component. I want to know that. So, if I say this axis is my f, so what are the relations between the k and f? So, what I said? I have divided maximum frequency by n number of sample. So, what is the maximum frequency? Is 2 pi. What is in hertz? Is nothing but a fs. So, I can say 8 into 10 to the power 3 divided by n is the length of the division, length of the each division. So, length of the each division is 8 into 10 to the power 3 divided by n, which is nothing but 8 into 10 to the power 3 divided by 10 to the power 3. So, it is nothing but 8 hertz. So, 2 pi by n means 8 hertz. So, if I say k equal to 0, that means 2 pi by n into k is equal to my f. So, k equal to 0 means 0 hertz, k equal to 1 means 8 hertz, k equal to 2 means 16 hertz, k equal to 3 means 24 hertz. So, I can say that I have divided the frequency scale every interval of 8 hertz. So, when I plot x0, I get 0 hertz. When I plot kx, this is the plot of x of 1, that is nothing but 8 hertz. So, this is called frequency resolution. So, frequency resolution of my discrete Fourier transform. So, this is my frequency resolution 8 hertz. Okay or not? Let us suppose my sampling frequency is 16 kilohertz. Then what is the resolution here? 16k divided by 1000. So, 16 hertz, so my resolution is 16 hertz. So, as I see that if I want to increase the resolution for a constant sampling frequency, I have to increase my n point DFT. DFT, length of the DFT must be increases. Is it clear? So, this is the relation frequency resolution of a DFT, discrete Fourier transform. Now, if I ask you that suppose I said this is my DFT equation, where omega n is nothing but let us say this one is my DFT equation. How many complex multiplication is required? If the length is n, so e to the power j omega n is nothing but a cos 2 pi by n minus j. So, it is nothing but in the form of a minus jb. So, a minus jb into x of n. So, how many? I have to n equal to 0 to capital N. So, I can say n number of complex multiplication is required for one frequency calculation. So, if k also varies in the dimension of n, so I can say, okay, I am explaining better way, take a new slide. So, I am saying, suppose I said x of k is equal to, n equal to 0 to n minus 1, x of n multiply by e to the power minus j 2 pi by n into nk. This function is nothing but a cos 2 pi by n nk plus minus j sine. So, I can say it is a form of a minus jb. So, if I write down this one, n equal to 0 to n minus 1 x of n into a plus j, a minus jb. So, I can say that to compute x for k equal to 1, let us k equal to 0, if I want to compute, then I require a n number of complex multiplication. For every k, or I can say for every k, I require n number of complex multiplication. Xn may be complex or may be a real, which is a plus j 0b or maybe in a, does not matter, or even xn can be a complex also. Xn can be a complex also. So, I can say whether the signal is real or complex, the number of complex multiplication for every k is n. Now k is also varies from 0 to n minus 1. So for n number of k, I can say I required n cross n complex multiplication. So to compute a DFT of length n, I required n cross n complex multiplication. That is the complexity of DFT calculation. Multiplication and also summation, I have to sum it. So that is the computational complexity of the DFT calculation. So if it is 8-point DFT, I required 8 cross 8 complex multiplication. Now suppose, as you know, suppose I want to multiply A1 plus JB1 multiply by A2 plus JB2. So if multiplication of a two complex number, how many real multiplication is required? A1 has to multiply with A2, A1 has to multiply with B2, B1 has to multiply with A2 and B1 has to multiply with B2. So I require 4 multiplication, 4 real multiplication. So I can say n cross n into 4 multiplication is required to compute a DFT. So if it is 8-point DFT, 8 into 8 into 4 complex multiplication is required. Okay. So those are the complexity of the. Now what I said, if I want to increase the frequency resolution, FS or frequency resolution, then I have to increase n. Now if I increase n, the complexity is also increased. So how do I reduce complexity to increase the frequency response, frequency resolution? Those things we will discuss. So we will discuss about the properties of DFT and we will discuss about the trade-off between the frequency resolution and how efficiently we can calculate DFT without employing n cross n complex multiplication. That is, have you heard about that FFT, fast Fourier transform? Fast Fourier transform is not a new transform. It is an algorithm to implement discrete Fourier transform in efficient manner. So FFT is an algorithm to implement discrete Fourier transform in efficient manner. So next class I will talk about the properties of DFT and also then I talk about the time frequency trade-off between the frequency transform and that computational complexity. All those things we will discuss. One thing before I conclude, just I want to show you another example which you may in the form of like this: x of n equal to delta n 0.5 delta n. So instead of writing x of n is equal to 1 0.9, here is the zeroth sample, I can represent it in this way also, delta n. So zeroth sample is delta n 1 and n minus 6 sample, sorry, there will be a lot of 0, 6th sample. So it is nothing but a 7th sample. So it is 7th sample, n minus 6. So n equal to 6, it is 1. So I can say it is 0 to 6. So 7th sample. So I can say if it is 0th sample, 1, 2, 3, 4, then 5, then 6, 0 and then 7th sample is 0.9. So what is the DFT? Again I can apply the same formula. So here I know the length of DFT required with 7th sample is there. So n equal to 7. I will talk about that even if it is not equal number, then also that can be calculated. So next class I will talk about zero padding, all those issues. So n equal to 0 to 7, x of n, so 7 point, so I take 8-point DFT. So if I take 8 point, number of sample is 7 and I take n equal to 8. 8-point DFT. But here number of sample is 7 sample is there. So, to equalize it, so we put 0 at the end of the sample. That is called zero padding. We will talk about it. So, I take the 8-point DFT. So, it is n minus 1, 7 delta n here I can calculate. If I plot it, take the mod of xk. If you plot it, this is of mod of xk, I think. Now, this is of xn. This is the plot of xn. This is the plot of xn. Xn has a 1 at 0th position and has an 1 at 6th position. 6. So, 0, 1, 2, 3, 4, 5, 6, 7 sample. 1, 2, 3, 4, 5, 6, 7th sample it is. Then I put 0 here, 8th sample. Then if I plot it, mod of x of k. So, if I calculate the mod k equal to 0, if I calculate, then if I plot it. So, this is 0th plot. So, k equal to 0 means this is 1, so this is 1.9, almost 2. K equal to 1 means you can calculate, k equal to 2 calculate, k equal to 3 calculate, 4, 5, 6, 7. Although the signal is up to 6 sample, here I can get 8 sample. Similarly, you can calculate the theta also, you can get this plot. So, this is theta plot. So, this is the angle of x of k, and this is the magnitude of x of k. So, that is nothing but a mod of. So, you can calculate the mod of it. Okay? Thank you.